Thank you to the organisers for inviting me. It's great to be back here. Before I actually start my talk, this is just a sort of an advertisement slide. So those of you here yesterday heard Eric Cavalcanti talk about some joint work with me, but I'm not sure if he pointed out that you can read almost all the details what he talked about in this paper here on the archive, which is eventually, I guess, going to be published in the Quantum Unspeakables 2, which is the conference proceedings from the conference last year here in Vienna for the 50th anniversary of Bell's theorem. And so something else which Eric mentioned was the loophole-free Bell experiment, which was just published a few days ago. And if you want to know my take on it, you can read the News and Views, which was published simultaneously with that in Nature. And if you want a second opinion, I recommend this, also by me, in the free online magazine, The Conversation. Okay, and it is actually a different, slightly different take on it, so it might be worth it. All right, but this is not what the topic of my talk this afternoon is. I've got for that this rather unwieldy title because it is going to be a rather unwieldy talk. But anyway, we'll see how we go. So yes, ensembles of Bohmian trajectories, real, surreal, and hyperreal, and explain as we go. So this basically the new work, well, relatively new work I'll be talking about here, is done with two groups of co-authors. So there's a theory paper with Michael Hall, who's with me at Griffith University, and also Dirk-André Deckert. I haven't attempted to put all the other affiliations for those people who aren't at Griffith University, which is for those who don't know, here in Brisbane, Australia. And the second collaboration is the experimental one with the group of Ephraim Steinberg, and I'll be talking again about one of the experiments that he talked about this morning. And so I guess I'll be saying a lot of the same things, but it's conceptually challenging, so hopefully no one will mind hearing some of those things again. Okay, yes. So here's an outline of my talk. I'm going to start, it was a challenge to sort of give a structure to everything that I wanted to talk about. And so I've done it in this way, talking about sort of some of the major approaches to interpretations of quantum mechanics. And although it might seem to be superfluous here, I thought I'd begin by talking about, why are we interested in realist interpretations at all? And then I'm going to talk about Bohmian mechanics as an obvious example of that. And why, some of the issues with that and how that relates to the nature of the Bohmian trajectories in the questions of are they real and are they surreal? Then I want to talk about the many worlds interpretation, and that's because what I want to get onto as the third topic is in some sense like combining Bohmian mechanics and many worlds. So maybe these are better together, and that's this new approach that we have been developing. And in a sense, this is where the hyperreal part comes from, because it's actually taking a Bohmian ensemble and taking it, saying that it's all real, so that it's even more real than the usual Bohmian mechanics, and that's why I call it hyperreal. Okay, so to begin with, so quantum mechanics. Orthodox quantum mechanics. So most of us here think that there are problems with quantum theory. Certainly hardcore gamer agrees that quantum theory has a lot of problems. Of course, I think he was probably talking about this. Anyway, so what do I think the problems are with quantum theory? So to put it very briefly, I think there are two big problems. One is the mathematical formalism itself, and the problem with that is that it's just very remote from the everyday world. But then the second problem is Bell's theorem says that we can't replace that problematic formalism by something which is, directly tied to the everyday world in terms of giving a local realistic or locally causal explanation of what's going on in the space-time sense. So that's the problems. What are the attitudes you could take towards that problem? Well, one attitude is just to be an operationalist and say, well, who cares whether the formalism is remote from the everyday world? All I care about is being able to predict the results measurements when I do them, and for that purpose, that's all that I need. The way I see it, the big issue with this operationalist or orthodox approach is that if you say that, well, I'm not ascribing any reality to the quantum world because all I'm interested in is the macroscopic world, well, then you have the issue that if we, the macroscopic observers, everybody doing science would agree that we are made up of atoms, etc., which are quantum particles. So how can it be that we, the macroscopic observers, are real if we're made up of things to which we're not ascribing any reality? Okay, so if that's the issue, then the obvious other attitude you can take is a realist attitude, which is to say that macroscopic observers are real in common with the operationalist approach, but they're real because there is a reality for all quantum systems, and they just inherit that from that. So the rest of the talk will be about talking about realist approaches, but it's worth distinguishing different types of realism. And in terms of what their attitude is towards the wave function. I'm not claiming that I'm being exhaustive here, but I'm going to talk about the types of realism that are relevant to my talk. Okay, so for my talk, it's going to be useful to think about this, the quantum state actually as a wave function, that is as a complex function on a high-dimensional configuration space. And so, yeah, if you have a bunch of particles, each of them has 3 coordinates, so you end up with this large number of dimensions in configuration space. But I can just write down a Schrodinger equation in that configuration space like that. And then, okay, in the what I'm going to take to be the first type of realist approach is to say that that is reality, okay? So that this wave function or pure state, despite its remoteness from the everyday world, is what is real, okay? And that's, I think, the many worlds interpretation, though there are variations. Another approach is to say, yes, that is real, but there is something else which is more connected with the everyday world, which is also real. And that's really where hidden variables interpretations fit in. And then finally, there's another approach which would say that only something else, so in other words, not the wave function, but there is something else which is connected with the everyday world, but obviously not limited to it, because it can't be, we know from Bell's theorem, and that's what's real, okay? And this is where the new approach that I'll eventually get to of many interacting worlds will fit in. But to begin with, I want to talk more about hidden variables, and so Travis gave a very nice presentation yesterday about Bohmian mechanics, which is really the canonical type of hidden variable theory, or sometimes called the de Broglie-Bohm interpretation. The only way I'd slightly differ from what Travis said would be to say not that there is more than just the wave function, the guiding equation. Really, to get the predictions of quantum mechanics, we have to put in an assumption that, in some sense, there's the typicality measure or probability measure for the position of the particle at some time in the past was given by the mod squared of the wave function. Okay, but then that's it. So it's a very nice theory. You can get these nice trajectories which people have been showing, and yeah, it all works very nicely. Okay, so is there a problem with the? Oh yeah, good, fixed. Okay, so why look any further than that? If Bohmian mechanics is explained everything and it's a nice realist theory, why don't we just stop there? So one issue is the question of, well, why would we believe Bohmian mechanics in particular to be real? Because there are, in fact, the infinitely many possible hidden variable interpretations, okay? It doesn't just have to be based on the position of, or the configuration of the universe in that sense. Now, in general, so Bell was, I think, the first person to think about this generally, and he showed that in general you have to write down stochastic equations rather than deterministic equations. So you might say, well, that's a reason to favor Bohmian mechanics. Okay? But even if you do that, there are actually infinitely many guidance equations which you can write down for the position, which are empirically adequate in the sense that they preserve the probability distribution which we know quantum mechanically should hold for the positions of the particles. Okay, so we can ask from the first question, why choose the configuration as being the real thing? the positions of particles and fields, etc. And the question, even if we do that, why would we believe in the particular dynamics that Bohmian Mechanics says? Okay. So this issue, I'm not saying there's a definitive answer to that, but we can at least address this issue and address it both in a theoretical and an experimental sense. Okay? So the theoretical sense, and Ephraim already talked about it wherever he is, over there, this morning, is that, so first, if we take determinism as something which we like in a theory, then we know that we can only do that if we have a hidden variable which has a continuous spectrum. Okay? If it has discrete, then it can only change by random jumps. Okay, so but what would be special about any particular guidance equation for one of these hidden variables? Well, what I showed in this New Journal of Physics article in 2007 is that if we think about if we imagine that we have as the ability to do weak and strong measurements, and we've heard quite a lot about weak measurements already, then if we define a velocity for a given preparation of a quantum particle, as well, there are different ways of doing it, as Ephraim talked about. I'll jump straight to the second one. If we just do a weak measurement of the velocity of the particle, if we imagine we can do that, and then condition on a strong measurement of the position of the particle immediately afterwards, okay, then that defines a velocity field as a function of where we found the particle, and it turns out that that comes out to be exactly equal to the Bohmian velocity field. So we get at least that dynamics uniquely in that way. There's a caveat that this only works if the Hamiltonian generating the dynamics is at most quadratic in operators canonically conjugate to the position. I suppose that should be a Q probably. But, and you might say, well, that's a bit of a limitation then. That's telling you this is not completely general. It's not always giving you the right answer. But I prefer to look at this as a feature because the point is that we know, in fact, the Hamiltonians in the world are at most quadratic in the momentum, which is the operator canonically conjugate to position. So if we choose, right, the hidden variable to be position, then this is all perfectly self-consistent. Whereas if we were to choose the hidden variable to be the momentum, for example, which is another example that we might have thought of, then we'll find that it's not self-consistent. Okay? So this doesn't prove, of course, that Bohmian mechanics is real, but I think it gives you a sense of the self-consistency and naturalness of Bohmian mechanics that doesn't exist for other hidden variable theories. So I think that's a point in its favor. Okay, so as I said, this can be addressed then both theoretically and experimentally, and I think this is exactly a picture that Ephraim put up from a paper from his group in 2011. I probably don't need to say any more about that. Except, well, okay, so that you can measure these trajectories and you get qualitative agreement with the quantum predictions. You see interference. It's all very nice. Okay. All right, so now the more challenging thing to talk about is this accusation that Bohmian mechanics is surreal, and that's a reason not to believe in it. And so this, again, is what Ephraim talked about this morning. So this was an idea that Englert, Scully, Sussman, and Walter came up with in 1992. And so this is the way I'm going to explain what they meant by surreal trajectories. So what we want to consider is three quantum systems. So particle one, and that in these diagrams, that's going to be described by its transverse position x and longitudinal position z, which is sort of a proxy for time, as Ephraim talked about as well. So particle one is going through a double slit apparatus. Okay, and so this is where they go through, and then over here we have the far field, or at least the mid field in the plane out here. So in addition to that, we have another quantum system, which is a which-way measurement device. Okay, so that measures whether the particle one went through this left slit or this right slit. And this, we're going to idealize that as just a qubit or a spin degree of freedom, something which only has two possible quantum values, which, for reasons of connection with the experiment, we'll call H and V. And that which-way measurement is made, arbitrarily early. You could think of that as being made already when the particles are passing through these slits here. Okay, but then we have a second or third system, which is a second particle, a Bohmian, something which has a Bohmian degree of freedom, a position, which I'll call particle 2, which we think of as being the pointer, okay? And the point about that is that in Bohmian mechanics, in standard Bohmian mechanics, spin is not a thing that has an independent reality, independent of the positions of particles. It's a thing which emerges, if you like, from, it's there in the wave function, but any reality it has is a consequence of the reality of the positions of the particles, okay? So in that sense, that although the which-way measurement information has been stored in the spin way back here, it's not real information until it actually moves the pointer, okay? Until it moves something which has a Bohmian position. And okay, now we finally get to the point, is that I can imagine that happening at different times, okay? I could arrange that the readout, okay, the thing that makes the information real, the readout of the which-way measurement information happens early, right, in this diagram. In other words, before the waves coming out of these slits have interfered. Or I can imagine it happening late. Okay, now, if it happens early, then everything is as you probably naively expect. In that, so the red is just all the trajectories, Bohmian trajectories here coming through the left slit. Or yes, that's right. And if you're making a which-way measurement, then of course you'd expect that you will lose interference. So there'll be no interference here. And in fact, the particles coming through this slit will eventually spread out over the whole plane, just as the particles coming through here would eventually spread out over the whole plane as well. Right, but the pointer will then be pointing down if they came through the left slit and up if they came through the right slit. So hopefully that diagram makes sense to everyone. But if we do the readout of the which-way measurement information late, in other words, that the pointer is only moved once the particle has gone into the midfield, as it is here, then what we see is not like that. What we see is that the particles actually do not, like the red and the blue particles here, do not cross the midline, which they are doing up here, okay? And up to that point at least. And the pointer can be pointing up or down even when the particle is going through just the left, through the left slit or through the right slit, okay? So because this is in the midfield, out here, the pointer is always pointing down, and over here the pointer is always pointing up. But in the middle, where the interference is starting to happen, you see that you can have the pointer pointing up, which should be indicating that the particle came from the right slit, when in fact the particle came from the left slit, okay? So this is the sort of unreliable measurement that apparently exists in Bohmian mechanics, in that you have a pointer saying that the particle went through one slit, naively saying it went through one slit when in fact it went through the other one. And so this is what Englert et al. Called surreal, the surreal behavior of Bohmian trajectories. Okay, so again, we can address this issue. And so Ephraim talked about the history behind the experiment. I'm not going to go over all that. I'm going to jump straight to talking about some of the details about how it was calculated. So as Ephraim said, we don't actually have a physical pointer 2 that we're tracking in the way that we'd ideally want. We're only looking at the Bohmian trajectories for one particle, okay? But we know the theory of how those Bohmian trajectories behave under these two different regimes, okay? Whoops, how do I get back? Of an early readout and a later readout. What do I press?
This one button you don't have. This one.
Don't press that. Yeah, okay. Thanks. Okay. Right, yes, of this early readout or the late readout. So if we're in the situation of a delayed readout, okay, where the particle has already reached the far field before we actually read out that pointer the information into the pointer, then Bohmian theory says that the velocity of particle number 1 as a function of its position and the pointer position is simply an average of what the velocity field of a particle going through the left, or a wave, the particle, if we only had a left wave and if I only had a right wave, it's simply the average of that. And that's also simply equal to what you would reconstruct using the weak value measurement, or the weak measurements, the values from the weak measurements, if I simply ignore the second particle altogether, okay? And so in the experiment, okay, so this is the way, just to remind people, though, it's done with entangled photons, which means that the polarization of photon 2 carries the information about which, in a quantum sense, carries the information about which slit particle 1 went through, and that this is the point at which these sort of virtual slits exist. Okay, so if we want to know what does the Bohmian trajectories look like in the case that we have a late readout, this is the case where it's supposed to be surreal, we simply ignore particle 2 and reconstruct trajectories in the usual way, just using particle 1. And what you see is indeed surreal trajectories, in the sense that we get trajectories here which don't cross. Okay, so you'd expect naively that, because we have which way information, that the particles coming from this slit are distinct from those coming from that slit, and they should just spread out. But that's not what happens. We have a no crossing condition, and but this is guaranteed by the way that the experiment is done. Okay, so that's not an amazing thing to see. The reconstruction technique is guaranteed to do that. What I think is more interesting in this part of the experiment is probing, or coming to an understanding of why it is that Bohmian mechanics gives these surreal trajectories, gives this unreliable information. And that's, as Ephraim talked about before, is that the polarization of particle 2 in the Bohmian sense, which is to say is just a function, this is just an expectation value of the spin of particle 2 as a function of these real things, which is the positions of x1 and x2, right? Turns out to be, in this situation, again, only a function of the position of particle 1, but the point about it is that it changes as particle 1 propagates, okay? So normally you'd think particle 2, the polarization of the photon, as, it doesn't depend on time. It's not going through any sort of, medium that would cause it to change. Nevertheless, as a function of the position of particle 1, the mean polarization of particle 2 changes, and so that in this particular case, it starts off down here in V vertical, representing on this side, but as you go through, it ends up in a superposition of H and V, which is reflecting the fact that, in fact, if you read out now in the HV basis to find out which slit the particle went through, it could be, that information has been lost at this point. You could get either answer. Okay, so it looks like some sort of non-locality, of Bohmian mechanics, that the behavior of a property of particle 2, right, is changing in time because of the way that particle 1 is propagating. Okay? And that's the explanation of why there really is an unreliable readout, because our intuition about quantum observables, that the polarization of a photon doesn't change as it propagates in free space, does not hold when that's a property of which is made real through the Bohmian positions. Okay, it's unreliable because you have this sort of non-local effect. Now, you might question that, is that really non-locality? And you could argue about that, but I think the best answer to that is that in this experiment, we even if you not convinced that that's non-locality, we've shown non-locality in the strongest sense in this experiment. So I've called this real non-locality, so just to use the word real again. And what I mean by that is setting dependence, okay? So what we're showing here is that by changing the setting for measuring one particle, we change the behavior of the hidden variables for the other particle, and that, of course, changes the outcome according to the theory, right? If you take the hidden variables theory seriously, that changes the outcome you get on the second particle as a consequence of changing the measurement on the first particle. Okay, so the point is being that this is not something that exists in standard quantum mechanics. You do not have setting dependence in this way in standard quantum mechanics, but you do in any realistic or hidden variable theory. Okay, well, at least a deterministic one, and a non-trivial one. So, okay, so to see this, what we want to do is move to the other regime, the regime of immediate readout. And in that case, it turns out that the velocity of particle 1, again, it's a function of the position of particle 1 and particle 2. The only thing that's relevant about the position of particle 2 would be which outcome it indicates, whether it's up or whether it's down, which is essentially or whichever way we read it out, essentially the readout of particle 2's polarization. We don't actually want to read out in the HV basis, okay? We want to read out in the quantum eraser basis. The reason for that is that if you want to see non-locality, the way we want to do it is to say, let's start a particle at the same, or track the trajectories of a particle starting at the same position and see how that's affected by the choice of measurement we make on the other side. Now, if we make an HV measurement, then depending on the outcome, it might be, it might be that you just don't have any particles there. If you're making a horizontal, if you get the result H, that would say that they all have to be in the right. And so, whereas if you get the result V, they'd all be in the left. And so we can't really compare the particles in that way. Whereas if we use this quantum eraser basis, so that's measuring in this basis, so it's the state theta or theta plus pi. So these are the two orthogonal polarization states. Which are defined in this way. So they're on so going back here, these are on the equator of the Bloch sphere here. So it's this pair or this pair. What we showed, as Ephraim said, is that, so consider the 0 and the pi, so that's one pair, which corresponds to one measurement, and so there you get either this trajectory or this trajectory, whereas if you measured in the other basis, right, the pi on 2 and 3 pi on 2, then you either get, depending on the outcome, this dark blue or the black, so the ones like that. So you see, you get completely different behavior of the particle 1, depending on the measurement you make for particle 2. And as I said, that's non-locality in the strongest sense that we've demonstrated. Okay. All right, so I'm going to have to go quickly. But as I said, I want to say briefly something about many worlds interpretation before getting on to the many interacting worlds. So I can relate this back to what I was talking about in terms of the wave function as followed, is that the wave function for remembering this is just the wave function for everything, wave function for the universe, is a very highly structured field in position, okay? And in particular, it's going to, if you do a bit of smoothing out, it's going to have local maxima at a vast number of macroscopically different configurations, which I'll call Q1, Q2, etc., with a little twiddle on top just to say that that's where the maxima are. So you could think of these as being many worlds, okay? This is not exactly the way it was first presented, but if I wanted to relate it back to the Bohmian, I think this is a clear way of saying it. So then as time increases, what you find also is that these local maxima are liable to split into, say, 2 or more other local maxima, okay, as time goes on. And this is exactly the sort of branching or splitting that Everett talked about in 1957. And so this is a cartoon of Schrodinger's cat splitting into the live and the dead branches here. Okay, so we'll probably hear more about this. It's a valid interpretation to say that's real, but why not just go with that? So I think there are a number of issues which can be raised there. First, it's not clear exactly what you're saying is real, and I think different people, different adherents to the many worlds interpretation actually have different answers. If you say that it is the wave function that's the thing that's real, well, then you have the problem that in some sense that wave function can just be represented by a vector in Hilbert space, and so then how can something just pointing in some vast dimensional Hilbert space represent the world? How can it have any structure? Okay? And in particular, because all it does in its dynamics is just rotate around the Hamiltonian direction. So yeah, it seems like that. Where do you find the world in that? On the other hand, you could say, well, let's look at these configuration space because that's where you can see all the structure in the many worlds. But then the question is, well, what exactly are you saying is real? If these maxima are real, well, how many maxima you have depends on exactly how you do this coarse graining, and when they split will also depend on that. So it's all a bit vague. There's no definite ontology there. Another problem is that is always going to be faced is that some worlds are more real than others. That when you get this splitting, the heights of the maxima, if you like, are not going to be equal. Well, that's only a very vague way of putting it. But the point is that you have different coefficients in front of this, of these two orthogonal states here. And we could have that mod alpha is bigger than mod beta, okay? Which in some sense says that this world is bigger than that world. But for the people in those worlds, it's going to feel just as real. So why should I, at the moment before the split, care about which world I end up in this particular ratio of mod alpha squared to mod beta squared? And I think I'll skip over that one. Okay, so Bohmian mechanics and many worlds, let's put them together, okay? So first of all, Bohmian mechanics in the light of the many worlds interpretation, a many worlder would well say that Bohmian mechanics, and this is an exact quote, is just many worlds in denial, because Bohmian mechanics postulates this wave function for the universe exactly the same as many worlds does. So if you're partial to many worlds, why would you add anything else? So in the Bohmian mechanics, the true configuration of the universe will typically be near one of these many worlds interpretations. One of these many worlds in the many worlds interpretation. So that leaves all these other maxima as not having an x associated with them. And so you could ask the question, well, what about all these empty worlds? Won't they feel real to the people who inhabit those worlds? And so this is just a little joke. So Lev Weidman once said, one of us, Lev Weidman, used to view the Bohmian interpretation as the most elegant way of pointing out one of the many worlds of the Everett interpretation as real, but then he changed his mind. And so here I have Lev. So this is a Bohmian particle inhabiting Lev over here, Lev going onto a beam splitter, and so then we get two copies of Lev in two worlds coming out. Only one of them is real, and that's the one that's saying, on reflection, I changed my beliefs. And the one who goes through says, I used to believe in this, but it left me with an empty feeling. Okay, that's the empty Lev, that's the empty wave, and this is called the empty wave problem. Okay, so what that's suggesting is that the problem with Bohmian mechanics is there's not enough reality. Like, why, if this is real, why isn't this, if this Lev is real, why isn't this Lev real? There should be, why don't we have a thing associated with that as well? And again, I think I'll skip over that. All right, so we can actually solve these problems if you believe that they're problems. All of these with this new approach called many interacting worlds. So a way to motivate that is just to look at this picture of the Bohmian trajectories for a two-slit experiment. And if you look at it, you just say, well, it looks like a bunch of particles which are repelling each other. So the question is, why not take that literally? And so the first person to talk about this in detail, and we'll hear from him later today, was Bill Poirier in 2010. But we didn't know about that when we started working on it. And there's a slight difference in our approach in that we actually imagine a finite but extremely large ensemble of worlds rather than a sort of continuum. But apart from that, the idea is very similar. Right, okay, so I want to wrap up as soon as I can. But so very briefly, maybe I'll just deal with the pictures. So this is the idea that we think of, let's start by just thinking of Bohmian mechanics, but where I don't say one of these trajectories corresponds to the real world, but I rather say all of them correspond to the real world, okay? But once I do that and postulate all these real Bohmian trajectories, then there's a nice bit of mathematics which says, at least in some limit, okay, that it should actually be possible to get the dynamics of that real ensemble of particles without using the wave function. Okay, if the initial conditions are right, I can postulate, so this is at least what we've done, at least as a toy model for this, to write down an explicit interaction between nearby worlds, right? So that all of these worlds are real. Okay, so there's nothing which can say that they can't interact, right? And so we postulate actually this is just Newton's equation, right? If I only had this potential, this is the normal Newtonian potential, then I just have Newtonian mechanics. But now I postulate this extra potential, this interworld potential of in this one-dimensional case of the worlds interacting with just the neighboring worlds on either side. Okay? And so that's a particular form in our toy model. And what we claim is that in the limit that n goes to infinity, we should recover the virtual Bohmian ensemble from this. So importantly, so there's no wave function in the ontology of the theory. It's just the whole ensemble of particles. These ensemble of worlds is real, not virtual, and they have to be real because they're actually interacting. Okay, so that's the many interacting worlds. So just to show that it does work, at least qualitatively, this is the exact solution for Bohmian trajectories for using the quantum wave function. And this is using no wave function at all, just an ensemble of trajectories interacting. And there are little differences, as you can see, but qualitatively, it looks pretty similar. And this is only with an ensemble of the number of worlds you see here. So I think it's 41 worlds here. Okay. So those of you here 2 years ago would have seen that I had a similar plot, but the right-hand side looked much worse. We got better numerics, and so it is actually much better than it looked 2 years ago. Okay, so we've done a bunch of other stuff. I think I'll probably just skip over all of that. We have a whole lot of open questions, but maybe I'll leave that and just finish my final slide just putting up a recapitulation of everything I've talked about. Thanks.